Good afternoon, and welcome to hand-wavy chemistry. When two molecules collide, if they do so with an appropriate amount of energy and the correct orientation, there is a chance that they will react. But chemists can't just put a whole lot of random molecules in a box, shake it up, and hope that something useful falls out. No. Instead, they need to understand how molecules react and be able to predict the products of those reactions. Before we tackle the subject of how molecules react, let's start by thinking about why it is that atoms bond in the first place. By considering the simplest of systems, two hydrogen atoms coming together to form a hydrogen molecule. On this diagram, the horizontal axis represents the distance between the two hydrogen atoms, and the vertical axis, that represents the energy in the system. When the two atoms are far apart, they are unaware of each other, but as they begin to come closer together, they begin to positively interact. The electrons see the nuclei and begin to attract. And as this happens, we descend down into an energy well. And as they come closer together, that interaction gets stronger. And we go down until we reach a point at which we start to come back up again. This is because at these closer distances, the nuclei see each other and they begin to repel, and we get this sharp, rapid increase in potential energy. So looking at this graph, we see there is a particular distance associated with a minimum in energy. And this will be the average bond length. Because our vertical axis represents energy, as we make our bond and we descend down into this energy well, energy must be released. And if we want to break the bond, we would have to put energy in to get the atoms apart. We'd have to get them up out of this energy well and away from each other. This is why we say that making bonds releases energy and breaking bonds takes energy. Now, from this simple bonding model, you might assume that molecules react to get to a lower energy, which would mean that all reactions are exothermic. But this is not true. And you can very easily rationalize this falsehood by thinking about fruits and vegetables. When we eat fruits and vegetables, the chemical reactions that occur inside our body release energy. However, when the plant was growing those fruits and vegetables, the chemical reactions going on were taking in energy. They were endothermic. And in the specific case of plants, the energy to power these reactions comes from the sun and occurs through photosynthesis. So reactions must be able to be both endothermic and exothermic. Something else that was brought up during our simple model was the positive attraction between the negatively charged electrons and the positively charged nuclei. Now this is important, and chemists will often classify different molecules or different parts of molecules as being electrophilic, meaning that they like electrons, or nucleophilic, meaning that they are attracted to the nucleus. And our nucleophiles are going to be attracted to areas with low electron density, so a slight positive charge. Meanwhile, the electrophiles are going to be attracted to areas of high electron density. And so, when these two moieties see each other, we can expect them to try and react. So one way we could consider a potential reaction occurring is by thinking about the polarity in the molecules, in the bonds. Which brings me to the question that inspired this video. The question related to the reaction of borane, BH3, with an alkene, a carbon-carbon double bond. And the specific question was, since hydrogen and boron have similar electronegativities, does it matter if the curly arrow showing the movement of electrons from the double bond goes to the hydrogen or to the boron. And one school of thought was that the end product looks exactly the same, so yeah, it's fine. But the dissenting view was that the lowest unoccupied molecular orbital, also known as the LUMO, is on the boron. In chemistry, there is this idea known as frontier molecular orbital theory that says when a chemical reaction occurs, the most important molecular orbitals are the HOMO, so the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital, and how they overlap and interact. And we would expect to see electrons being transferred from the HOMO to the LUMO. And that is what was meant by the statement that the LUMO is on the boron. And indeed, if we calculate the molecular orbitals for borane, we see that the LUMO is an empty p orbital on the boron. And so that is where the electrons should transfer to. And the curly arrows we draw to represent this reaction should look like this. Now for another example, cyclopentadiene. This molecule is very hard to isolate because it loves to react with itself. And if you only thought in terms of polarity, you might think that it is the oxygen, being the most electronegative element, that is going to be involved in this reaction. But if we calculate the HOMO and the LUMO for this molecule, we see that both of them relate to the carbon-carbon double bonds. And indeed, this is the reaction that we see, dimerization through a Diels-Alder type pericyclic reaction. And speaking of pericyclic reactions, the researchers Woodward and Hoffmann were researching the stereochemistry associated with an intramolecular pericyclic reaction, and developed a set of rules for predicting what the product would look like. These reactions involve a chain of alternating carbon-carbon double and single bond. And the simplest molecule that these rules apply to is buto-1,3-diene. If this molecule were to take part in an intramolecular reaction, that is, react with itself, closing up to form cyclobutene, then those terminal CH groups would have to rotate to facilitate the formation of the new bond. This rotation could either be in the same direction or in opposite directions. Woodward and Hoffmann determined that for an even number of carbon-carbon double bonds, the rotation was conrotary. Both molecules rotate in the same direction. But for an odd number of carbon-carbon double bonds, the process is disrotary. They rotate in opposite directions. We can understand why this is by examining the HOMO for these molecules. And for the sake of clarity, I'm going to only show the individual p orbitals that comprise the HOMO rather than showing the combined orbital by adding them together. If we look at the p orbitals on those terminal CH2 groups in buto-1,3-diene, we see that they are in opposite orientations. When a bond is made, we need to overlap orbitals that are in phase. So in order to bring those orbitals together, they must both rotate in the same direction. Now, if we were to look at hexa-1,3,5-triene, we see that those terminal p orbitals have the same orientation. So to bring them into a positive overlap, they need to rotate in opposite directions. Adding even more weight to this molecular orbital explanation is the observation that if you irradiate these molecules with ultraviolet light, the rotations reverse. Conrotary processes become disrotary, and disrotary processes become conrotary. This is because the UV light promotes an electron from the HOMO into the LUMO. So now that LUMO is our HOMO. And if we look at the terminal p orbitals for this excited state of butyl 1,3-diene, we see that they now have the same orientation. So that is why it must now be a disrotary process when before it was conrotary. What we are starting to see here is how understanding the electronic structure of the molecules and the molecular orbitals can provide an insight into the mechanism by which a reaction occurs. And so, as one final example, I want to discuss the nucleophilic substitution reactions that occur with alkyl halides. When a molecule like bromomethane reacts with a nucleophile, the bromine leaves, and the nucleophile creates a new bond. However, if we pay particularly close attention, we actually notice that the other atoms that were attached to the carbon invert their positions. They're like an umbrella that turns inside out. We can understand why this occurs when we look at bromomethane's LUMO, and we see that the orbital available for a nucleophile to come and attack is directly opposite the carbon-bromine bond. So as that nucleophile comes in, it puts its electrons into the LUMO, which then weakens the carbon-bromine bond. It leaves, and all those other atoms that were attached to the carbon have to flip up to make space for the new molecule. However, if we look at a more sterically hindered alkyl halide, such as 2-bromo-2-methylpropane, that LUMO is no longer accessible. The nucleophile cannot get its electrons in there to kick off the reaction. And if you're looking at thinking, oh, maybe there's a little bit of room, this is what it looks like if I do a space-filling diagram. There's no way those electrons are getting in. But these molecules are still observed to react, so there must be some other mechanism involved in this type of nucleophilic substitution reaction. And indeed, there is. The process begins by the carbon-bromine bond breaking. And this is one of the limitations of molecular orbital theory. Because we spread our orbitals across the whole molecule, we don't really have a good way to talk about the strength of a particular bond. But we can use valence bond theory to say that, yes, this makes sense, this would be the weakest bond. It is thermally possible for it to break and come apart. So let's start by breaking that carbon-bromine bond. As the bromine moves away, it takes its electrons with it and imparts a positive charge on the carbon atom. The other methyl groups begin to rise up and they adopt a trigonal planar geometry around the central carbocation. This trigonal planar geometry might look a little bit familiar to you. The borane molecule we saw right back near the start of the video also had this trigonal planar geometry. And in fact, if those methyl groups were hydrogen atoms, these two molecules would be isoelectronic. They would have exactly the same molecular orbital makeup, which means even without performing any calculations, we already know where the LUMO is. It is on that central carbon atom. It is the empty p orbital. But this time, in addition to being somewhere that we can just accept electrons, that carbon is positively charged, so the reaction occurs very quickly. These two different nucleophilic substitution reactions are known as SN2 and SN1 respectively. The SN part of that name stands for nucleophilic substitution, and the 2 versus 1 part of the name refers to how many molecules are involved in the rate determining step of the reaction. But what is a rate-determining step, and what other factors can influence the speed of a reaction? Well, that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.